Okay, let's strive for an on-time departure of this session today. So good morning, good afternoon, good evening, depending on where in the world you are today. Welcome to the next session in this ATM seminar conference. Hope you've had a good first couple of days. My name is Tom Reynolds. I work in the Air Traffic Control Systems Group at MIT Lincoln Lab, just outside of Boston in the United States. And I will be chairing the session today. So without further ado, let's launch into our first presentation. It will be by Marie Carré. Marie works with Swiss Airlines in the operations department, responsible for all the innovation projects and collaboration with external partners, including industry, ATM stakeholders, universities, etc. Marie is doing a PhD in parallel with her full-time job. Her PhD is being done at the University of Clermont-Ferrand, developing a new approach for the optimization of Lufthansa Group airline operations during major disruptions in ATM. And Marie's talk is entitled Equity Within Air Transportation Management, an Analysis of Inequality Index for Multi-Stakeholder Optimization. So Marie, over to you.
Thank you very much, Tom, for the introduction. I'm gonna share my slides. Just tell me if you can see it.
That looks good, Marie.
Perfect. So thank you everybody to be there for this presentation about the equity within air traffic management, and more focusing on an analysis on the inequity index in the use case that we have, which is the multi-hub stakeholder optimization for airlines. I'm Marie Carré, and my co-authors that I would like to thank for their work too on this article are Séverine Durieux and Laurent Pietrac from the University of Clermont-Ferrand, and Eric Nantier from Swiss too. I will first give you a little bit of the context in ATM, but also in our PhD research in our use case. Then I will deepen a little bit in a very simple use case to illustrate the inequity indexes. And then I will go through a literature of the different inequity indexes, which could be very interesting for our research, and then go through this illustration on the simple use case before concluding. So let's start now with the context. If my slides, yeah, perfect. So within the ATM, there's several priorities. And the first one, of course, is safety. We have to fly our flight safely, and we have to be sure that no problem could occur. And then we have the efficiency, and we reach levels of congestion in the European ATM and US ATM, which were pretty high the last years. And that's something we need to cope with. And the problem is, if we have a congestion, then we have delay, of course, and then how to deal with this impact of the congestion on all stakeholders, which are mainly the airspace users. So these three priorities are subjects that are under research by a lot of different projects. But until now, the main way of taking into account this equity and this efficiency are, so from the European side, it's from the NMOC, so Network Manager Operation Center, from EUROCONTROL are taking into account the average delay minutes and try to just split the delay among the flights which are in the same congestion. And from an ANSP's point of view, it's really the first come, first served rule which is applied. And from the US side, from what we read through the literature, the first come, first served rule is of course also enforced there. And there's also the ground delay program that I will deepen a little bit later on. However, for airspace user, two flights doesn't have the same value. We have passenger flows with high valued passenger, or a lot of groups of passenger who has a connection. We have crew that have also rotations that have duty flight time limits. We have also the aircraft having rotations. We have maintenance events. We have many constraints, and two flights which could appear are exactly the same are really different for us as an airline. And that's something that Nadine Pilon in a lot of articles from UDPP also highlighted, and that we continue to highlight as an airline, that two-fly doesn't have the same value. For the next minutes or 30 minutes of talk, I will refer with a special definition of equity so that we are all online on that. It's a fair and just distribution of the benefits among the actors. So let's speak about the initiative which has been done for now to get more flexibility and how equity is kind of tackled here. So we have the user-driven prioritization process, which is aiming at allowing slot swapping among the same fleets of the same airline to get more flexibility and then to be able to rearrange the sequence. Here, the equity is as long as we are not touching other and we are not having a negative impact on other airlines, then it's fine. But then it reduces a little bit the flexibility. In extreme, that's an arrival process that we developed here in Zurich airport, sorry. We just, among our own fleet, we are giving a target time over, and then we can steer our all arrival from long haul, which reduces a lot the holdings and the vectorings thanks to this flexibility that SkyGuide is offering us. And of course, then reducing the impact on the environment. So here we can do that because once again, we are the major hub carrier here. So we are not impacting the other airlines, and the other airlines also arriving at the same time also are part of this system. We also have within the NCM project, there were the ATM portals from the MUAC colleagues who just allow us to give some priorities, so give some flexibilities. And if the ANSPs can do something, then the FMP will try to reduce the delay. But then is that equitable? That's also a question. And we got many examples of all the summer 19 initiatives from the NM who try to, out of this capacity, congested capacity, how to do the best and so on. And from this side of Europe, we also have the other side, which is from the US and really focusing on the green delay program. So the first one article is about the deviation of the slot, so that's airport slot allocation, so that's not dynamic. And it is assessing the deviation of the request from the airlines and what they received, and it gives an idea of the equity. And other articles also assesses the deviation always, so either from a baseline with no constraint, for example, or just assess the number of changes in the initial baseline or the time deviation and so on. So there's always kind of equity measures, but it's always on delays, and it's always on minutes of delays or first come first serve and so on. And now we have always more traffic, and the COVID didn't stop that. We still have already congestion in Europe, and we need this flexibility, and we need to grant the flexibility as much as we can, but also take into account the equity. And this equity consideration, if we are taking a strict consideration of equity, this will hamper the flexibility and the best use of the capacity. So the big question is, how could we have a definition of equity which allows us to have a lot more of flexibility in our system, ATM system, but also having the trust of the stakeholders that the balance of equity on a long term or anyhow is granted. And that's something that we retrieve in our multi-airline optimization disruption. During disruption, we have many airlines, so Lufthansa Munich, Lufthansa Frankfurt, CityLine, Austrian, SN Brussels, Edelweiss Swiss. We have many airlines, Eurowings. And if we have a disruption and we have to cancel, for example, 20% of our flight in a virtual hub. So for us, a virtual hub is an outstation with more than 25 rotations of the Lufthansa Group airlines, which means we have flexibility to try to share the resources and so on. So let's say we have a cancellation, we need to cancel 20% of the flights. So if we are just staying as we are doing now, each airline will try to then cope with this 20%. For example, for Brussels Airlines, they have to cancel one flight. So you cannot cancel one flight if you don't cancel the return one. And each airline will have to then cancel that. And our hypothesis here is to say, if we are sharing the resources of the entire Lufthansa group, so mainly the seats available on all the European and long-haul flights, and see with the flow of passengers, which will be the best solution, the optimized solution of reallocating the passengers and cancel this 20% of flights, but not each airline 20%, but maybe one airline 50% and the other only 10 or something like this. But if we are doing that, some airlines will be hampered and then disadvantaged in comparison with the others. So we need to have a calculation of equity, which is really like clarifying who got a disadvantage, who didn't. And we have to record that to be sure that at the end, the balance is stable. So at the end of a cycle, at the end of the season, we don't know. And so because of this balance, long-term, we could then say, we could incentive the people, the airline, to also accept at some situation to get less advantages than the others, and then have the contrary situation maybe 1 week after. So that's really the goal of our research here. And we set the first steps there by checking through the literature what is existing now. And mainly in the poverty, so in economics fields and public transport planning fields, there's a lot of indexes, and we will present you 3 and then the short analysis on it. But before that, there's different approaches from a perspective of equity. You have a utilitarian one, which is maximizing the total benefits of the group. So let's say for our group of airlines, we don't care which airline is advantage, disadvantage. We just want the most benefits possible for our group. We have the egalitarian one, which is then aiming at equalizing each benefit of each actors. So we all should then cancel this 20% and have the same impact on our operations and so on. We have the contractarian, according to a contract that we could do during between the airline. One could say, okay, I'm agreeing to, I don't know, participate, but only I should have a maximum of impact of 20% of my operation, something like this. And we have a sufficientarian approach, which is to say, each airline needs to have a sufficient level of operation which are granted, and then there's room for optimization. And from the literature, there's a lot of research about this equity index, and there's some rules to respect. So the normalization one, which is an index for inequity or equity, should be 0 if the perfect equity is reached, and otherwise it should be positive. We have also the symmetry. So which airline or which stakeholder will be hampered and the other advantaged. If the situation is just as if then the stakeholders hampered is the one advantaged exactly on the same proportion, then the index should remain the same. We have the Dalton population principle, which is about the invariance of the index if we replicate the population. We have the Pigot-Dalton transfer rules, which is if so it's really like if we take this economics field, if one individual is richer than the other and is transferring some money to this poor individual, then we should see that in the index of inequity. And we have the continuity. So of course, if we have a small deviation in the share of salary, for example, then we should have also a small deviation in the index. And we have the relative invariance, which is if we are just multiplying all salary by one constant, then the index should remain the same. So now let's deepen a little bit in the different equity index existing. So we have first the Gini one, which is the historical one. And the Gini one on the right of the screen, you can see the cumulative distribution of income according to the cumulative distribution of population. And that's the Lorenzo curve that you see here. And this blue line is the perfect equity. And the Gini index is the area A that you see here divided by this area of the perfect equity. And this gives us an idea of the equity and an assessment of the equity. And if you transfer it mathematically, then you can see here the Qe either being the salary or maybe the elementary performance for the airline that we're considering. You can see that it's the difference, the absolute value of the difference between two airlines, and then divided by twice the number of airline and the average of the salary. And the maximum value of the Gini is 1. So that's the first index. The second one is the tail index, which is based on the entropy principle, as you can see here. Here, the average of a salary or average of elementary performance is mu here. And the maximum value here is ln of n being the number of airlines or number of individuals. Here, which is what is very interesting in this index, is that the use of ln is more sensible to the airline which are disadvantaged. Because if you have a salary Xe, which is lower than this average salary, then the ln decrease for faster because it's scale 1. And if this salary is higher, then it increases but slowly towards infinite. And that's really something that we will see later in our use case, which is very interesting for us. And the third index is the Atkinson Index, which is aiming at an equity in the welfare rather than exactly in the income. And what is very interesting in this index is the epsilon, which is the aversion to inequity. And then you can model the decision maker sensitivity and saying, I don't care if it is equitable or not. I just want the best for the group. Then you will just set an aversion of inequity at 0. But if you just say, oh, what is the most important thing for me is really to be really equal, and that the situation is equitable between all other stakeholders, then you would have an aversion to inequity, which can be 0.5, 1, or even infinite if you're really, really willing to. The maximum value of Atkinson is 1, and we will see also in the further slides that it is also something important for us to find the right epsilon. So now let's deepen a little bit in the different solutions. So that's a very basic use case, because the aim here is to illustrate very clearly each behavior of each index. So it's based on the number of canceled flights and based on the passengers impacted by this canceled flight. So here you can see each time you have the 5 airlines and you have number of planned flights at the beginning, how many are canceled, and so on. Same for the passengers. So we'll go through each situation so that you understand the meaning of each situation, and then we will assess the inequity index. So the first solution is A. That's a realistic solution that we got from an optimizer, and which is balancing really well the repartition of the cancellation according to the flights, which are also having a lot of passengers and so on. The second solution is a very extremely imbalanced solution, because one airline, which is Swiss here, is canceling 10 flights over 10, so is operating 0 flight at all, so having a 100% impact on its operations. The third one, so solution C, is also an extremely imbalanced situation, because Lufthansa Munich is canceling also the 10 flights in the name of the group, but still have 4 remaining flights that they can then still continue to operate. The solution D and E are exactly the same, so the same flights are canceled, except except for Essen Brussels and for Lufthansa Munich, who are canceling 2 flights which are fully booked. And the other flights in solution D and the other flights of the other airlines in solution E are averagely booked flights. And then in solution F, you can see that only half of the airline are undertaking the cancellation for the entire group, And finally, in the last solution, G, every airlines are participating and canceling flights except one. So if we deep dive a little bit, we will start with the Gini index. You can see that the Gini index has the required sensitivity to see that the solution B, where one airline is canceling all its flights for the group, is very inequitable in comparison with the solution where one airline is canceling everything but still having 4 remaining flights to operate. Then you can also see, and that is a specific thing from a specific behavior from Gini, that a solution in which one airline is canceling 10 flights but still remaining with 4 ones is considered to be less inequitable than a solution where all of the airlines are canceling flights. And that's something which is very important for our further assessment. If you check, so on the right, on the left, you have the indexes from Gini about the cancellation, and on the right, the one calculating on the impacted passengers by the cancellation. And here you can see from solution D and E, of course, the same number of flights, so 2 per airline, are cancelled. You don't see any differences, of course, in the cancellations, but here you can see it because 2 airlines are canceling fully booked flights. And you can see that you have a sensitivity here. And here it's also the first big step to say we need absolutely an equity index, which is taking into account multi-criteria, not only about delay, not only about cancellation, but taking into account different aspects of the operations to really assess the global impact of inequity. And finally, on Gini index, you can see that, if one actor is canceling for the entire group, and if everybody is canceling except one actor, it is considered to be more inequitable than having only one not participating. And that's also something that you need to be aware of if you want to use this index. So that's a very equitable approach, so egalitarian because of this absolute value. And then it has the same sensitivity for favored airlines and disfavored airline. That's something also we need to take into account. And it has a specific behavior considering that one airline canceling for everybody is less inequitable than all airlines canceling except one. So that's something we need to be aware of. If we now go to tail index use case, so you can see that the solution A, which is an optimized one with a share of cancellation, is almost reaching the perfect equity, which is 0. If you check on solution B and C, one again being like canceling 10 flights and operating only 10 flights, so full impact on the operation, and the other canceling only 70% of the operations, you can see that there's a sensitivity here from the index that is important. You can also see between the solution D and E, so for the passenger, with D being averagely booked flights and E getting 2 airlines with fully booked flights cancelled, you can see that it's twice the inequity value here in solution E than D. And that's something we are requiring also. So for tail indexes, it is clearly differentiating the disfavored airline and the favored airline. That's already something we could see from the mathematical formula. So it has more sensitivity to the disfavored one. And actually, it's a human trend that we are always more affected by loss than by gain. And as we are trying to modelize the decision maker sensitivity about this situation and the long-term equity, that's something that we need to take into account. This tends to be affected by loss more than gain. And finally, what is really good for us is that you can very easily decompose the tail index. And by this way, you can really clearly identify which airline is bringing which components in the total inequity. And that's something which can be very interesting for a long-term and a multi-criteria calculation for an inequity index. And finally, the Atkinson Index. So you can see we have several, we did this calculation for several aversion inequity for inequity. So 0.5, 1, and 1.5. And you can see there's really a trend, of course, it seems the same situation seems far more inequitable with a bigger aversion, of course. You can see that this solution where one airline is canceling for everybody, for the entire group, and canceling all its flight is reaching the maximum of the inequity index, which is 1 for the Atkinson Index. And yeah, it captures also the difference. Then one is canceling 100% of the flights, and the other is canceling for everybody, but only 70% of its flight. And finally, you can observe that the Atkinson Index for the aversion of inequity, which is 1, fluctuates around twice the values for an aversion of inequity, which is 0.5. So it gives an idea of the sensitivity of this aversion criteria or parameter. So to conclude on the Atkinson Index, the aversion to inequity modelization is very interesting because you can really model this human and specific sensitivity to the inequity in this situation, given situation. Of course, if we have no inequity aversion at all, the index will be always 0. So we didn't put that in the article, in the table, because it will have been 0 everywhere. It reflects then the sentiments of injustice that is experienced by the airline, and that is what we try to model, because we need to give an adequate value of inequity that the airline can validate, so that we can then do the calculation in the long term. However, the decomposition of the Atkinson Index is really not easy. There are some paths in the literature who are trying to propose some way of doing, but it's not really clear how to continue with the Atkinson if we would like to decompose it. So now, based on this illustration of our basic use case, we can already discuss a little bit of the free indexes and set the path forward. So as we said, the equity for disfavored airlines more than favored airlines is really important for us. And already it just discovered the Gini one, which is a very egalitarian approach. If we are willing to modelize the human behavior being more sensible to loss than gain, we can use the tail index or the Atkinson index. And if we would like to have a decomposable index, we can take the tail ones. The Atkinson is not working. However, Atkinson index with the inequity aversion modelization is really important and can really help also in the comprehensive assessment of inequity. And it differentiates clearly the level, the different level of inequity according to the situation and maybe according to the operations of each airlines or each airspace user. So to conclude, the goal and the contribution that we try to publish in this article is first to propose the path for a new paradigm for equity calculations, not stay on this inequity calculation just based on a deviation in the delay or a deviation in the slot allocated or something like this, but go more into a multi-criteria based inequity calculation, because as we highlighted, it's something that we need because it just highlights the different aspect of the operational situation. And we need a long-term assessment, because if we are just considering the equity in one shot, in one iteration, then we will lower the flexibility that we have in our use case, which is the optimization of multi-hub airlines. If no airline can be slightly hampered at one situation and that everybody needs to be having the same equity level, we will just like throw out very good solutions, sorry, for the entire group, just to try to ensure that. So it's really something that we need to put efforts on in the research, also in European and US research, so that we can try to to set the path for long-term assessment of inequity. We would like to propose, several indexes and propose the adaptation of this Tail and Atkinson and Gini indexes to our very simple use case. And this is something that we could also, of course, use in the ATM for the equity assessment. So yes, we are not applying the results only in our fields of research, but also we could apply that more broadly. And we would like, yes, to set the path for further long-term equity guarantee, and in order to enable more flexibility and then have a better use of our congested airspace. And finally, we have further research path horizon from this first study, and we will need to spend some time more about all this consideration. So first is how to combine all these multi-criteria from the operations into the inequity measurements. That's the first question. The second one is how to calculate and propose this long-term inequity balance, inequity index, so that we can assess the balance of inequity over a cycle. It could be a month, it could be an ARAC cycle, it could be a season, it could be something else. And how to get the trust of all the actors who will see this assessment of inequity and really get the trust into these balance calculations. Because if we don't have the trust of the stakeholders, it doesn't make sense. They will not accept to play with this kind of global optimization. And finally, how to combine the Tail and Atkinson indexes, because they both have very good advantages. And one can be decomposable, the other has this aversion to inequity modelization. They are sensitive to disfavored airlines and so on. So that will be the third path of research, to say how could we combine it to get the strength of that indexes, and try to propose a new index which is aiming at the multi-criteria index calculations and long-term calculations. And if you are interested, here are some references. You have some more in the article. If you have any question, I will be very happy to answer it. And if you have any question further about the article or anything, just don't hesitate to reach out to us, and you have all the email addresses in the article. Thank you very much for your attention.
Okay, thank you, Marie. Very interesting presentation. Encourage anyone who has questions to enter them into the Q&A feature at the bottom of the screen. I don't see any initially, so I'm going to take the session chair privilege and ask you a question myself. So, so I think you've done a really nice job of detailing all the different types of measures that can quantify inequity, and I think the scenarios you highlighted really were interesting, bringing out some interesting features between them. I guess ultimately you'd like to use this in an operational setting. I know that you work in an airline operations group. Exactly. So how do you see the pathway here of evolving this R&D into sort of an operational setting? What are the major challenges to doing that?
So the major challenge is to get the trust of the different airlines into our calculations. And that's why we are doing research on that. We cannot just come with one calculation and say, hey, that's the equity calculation, and that's all, and that's like this, and just trust it. We cannot. We really have to set the path there. And so as we said, we are a group of airline, and we are having constantly disruption in our virtual hub. And that's really something for us, which is bring a lot of added value, and for our passengers too. So if we are not able to propose a global optimization to everybody, to all airlines for our passengers, and that we are not able to grant that the equity at the end is there, and to prove it really accurately to each airline's operational expert who will play with this simulation, who will play with this optimization, then it doesn't even make sense to try to implement it. So that's why we're focusing so much on this.
So you're ultimately then envisioning that to get to a point at some point where there are sort of these indices that have been pre-agreed upon by all the stakeholders, there's some real-time dashboard of the inequity metrics for an operational day, say, and if all the users have the trust that the system is truly representing fairness to all users, that will then help in the negotiations or the agreement of what to do on an operational day.
Exactly. We are planning of having a lot of iterations of this optimization and storing all these inequity elements of performance. And then each time we will have a new iteration, this imbalance, that's calculation that we need to do, will also play a role in the optimization. Because if one airline is always disadvantaged, then maybe we will give more weight into this multi-criteria optimization. So that's something we could envisage, and that's something which needs to be recorded and also take into consideration the different strategy of the group. So, for example, if we have one airline having struggle in one hub because a competitive airline also is operating from this hub, maybe we will try to favor this airline more. And even if the inequity balance is not fair, it will be the strategy of the group. And then it will be also from the manager of the operations to take this into consideration and accept that.
Okay, yeah, no, it's a great objective to have. I mean, it's incredibly complicated, as just from the examples, the simple examples that you've shown sort of highlight some of the complexity, but different airports, different airlines, different ANSPs are going to have different objective functions, right? And so their definition of equity for them may be slightly different. And so getting everyone to agree on what equity actually means is probably half of the battle, right?
But it's a key element, because if we are not reaching calculations of inequity in ATM, we are still struggling and reducing the flexibility. And if we could grant this equity long term, then it means that we could do the best out of the capacity which is existing.
Okay, great. We have one question just come in. So have you had any type of prototype interactions or run any test cases with airlines during live operations, or do you have plans to interact during live operations as a test in the future?
So for now, we don't, unfortunately, because it's still the beginning of the PhD, but we aim at having a prototype, which is on live data feed, and then to show really in a disruption what is the advantage of this global optimization module, and do the difference between what would happen without the coordination and what will happen with the coordination. And then as soon as we then get the trust of the operational expert, we will put it into production.
And you have the advantage of being an operational expert yourself, right? So it's
exactly, it's helping a lot.
You have the subject matter expertise readily accessible to you as well, which is great. All right, we have a couple of minutes. Any other final questions before we move over? I don't see any others coming in. Check the time. I think we're about 60 seconds away from needing to hand over. So I guess, Marie, thank you very much. Very interesting talk. Good luck with the PhD.
Thank you very much.
We'll look forward to seeing additional results from your work at subsequent ATM seminars. We're at 9:50 by my clock. So welcome to the second paper presentation in this ATM performance measurement session. So our next speaker is Qe Liu. Qe is a PhD candidate in the Transportation Engineering Department at the University of California, Berkeley. Qe's research interests include air traffic flow management and system performance, flight behavior prediction, and statistical modeling. Qe's presentation is entitled Miles, Intra-Hour Restrictions and Aviation System Performance, a Chicago O'Hare Case Study. Okay, over to you.
Okay, thank you so much. Hi, everyone. This is Qe Liu. Thank you for listening to my presentation. Today, I'll present you with one of our projects on mile intra restrictions. and the Aviation System Performance Chicago, Ohio case studies, supervised by Professor Mark Hansen. This is today's agendas. I'll first give a brief introductions on the background and project objectives. Then we will go through the approach and methodologies. Next, I'll cover the data set and some statistics, and then I'll discuss the model result. In the end, I'll give a summaries and talk about the ongoing research. Now let's move to the introductions on the background. When we're talking about the air traffic management, there are basically two components. One is the air traffic control, the other is traffic flow management. So when traffic demand is expected to exceed the capacities at a given air component, such as airport or the en route sectors, traffic manager will apply different kinds of traffic management initiative to manage the downstream constraints and to ensure the safety and the orderly movement of traffic flows. So here is a list of commonly used TMIs nowadays. Now let's see some general statistics of TMI operations. In 2018, over 340,000 TMIs were implemented in the US, and the frequency of each TMI is shown in the left chart. MIT counts for over 50%, which is about 200,000 restrictions issued. The red bar chart here represents the annual counts of MIT issued from the top 20 airports in the US, and we can observe that ORD airport released the most MITs, which is more than 10% of the total operations. So our focus is on the MIT restrictions. Let's have some basic information on it. MIT is a distance-based metering restrictions, which set the number of nautical miles required between the aircraft flying through certain locations. While vast majority of MIT are airport sourced, which is to say the ultimate cost is an imbalance between the demand and capacities at arrival airport. And during the operations, MIT restriction can be propagated upstreams from one facility to one or more facilities when the control center could not absorb the delay required. This procedure is called passback MIT. The passback MIT is still MIT sourced in this case, although it may apply the space requirement on an en route waypoint, but the ultimate cost is the imbalance at the arrival airport. When facing an MIT, flight could experience departure delays, speed control, vectorings, and holdings, and the MIT can be implemented independently or in conjunction with other TMIs. We believe ideal MIT shift the necessary delay to the locations where it can be absorbed efficiently and safely without sacrificing any throughput or increase any arrival delays. However, in the real practice, we do observe some deficiencies from the report and the literatures. First, an MIT could be set incorrectly. Frequent errors include having the MIT be activated for a longer period of time or setting the larger spacing requirement than actual need. Second, the value of spacing is a multiple of 5 nautical miles, which limits the ability to precisely calibrate the spacing to the available capacities. Third, the settings of MIT highly depends on the predictions of traffic demand and airport capacities. So the uncertainties in the national airspace and the inaccurate predictions could lead to wrong settings. So observing those deficiencies, we aim to assess the real-world performance of airport-sourced MITs. Therefore, for a set of such MITs, we will estimate the loss in the airport arrival throughput from the underutilizations of airport capacity caused by MIT, the increase in arrival delay resulting from MIT, and the airborne delays resulting from the MIT. We name these airborne delays as the queuing delay savings in the later slides. Okay, now let's move to the approach and the methodologies. In general, we will construct the airport queuing diagram for two scenarios. The first one is baseline scenarios, which includes the MIT operations. The second one is the counterfactual scenarios in which the MIT restrictions were removed. And then we will compare the queuing and arrival delays under these two scenarios, as well as the airport throughputs. We will choose the MIT operations of the ORD airport for the whole year of 2018 as our case study. Okay, let's see the illustrations on these two scenarios. For the baseline scenarios, which is the actual system performance with MIT in operations, each flight will have a planned arrival times and actual arrival times at the airport. The planned arrival time refers to the time aircraft would touch down in the absence of capacity constraints, and the actual arrival time refers to the actual wheels on times. Then we have the times for each flight during a certain period of times. The queuing diagrams can be developed. We can develop the queuing actual arrival curve A of t, and the planned arrival curve P of t along the times. And the orange areas between this curve represent the queuing delays in the operations. Next, we want to estimate how these two curves would perform in the absence of MIT, which is our counterfactual scenarios. As we remove the MIT restrictions from the flights, we assume the corresponding MIT delays will be eliminated from the flight as well. And these flights will have a new model planned arrival times. And we can derive the model planned arrival curves along the time. Then the flight will join the queue earlier and land earlier under airport capacity constraints and first come, first serve assumptions. As a result, a model actual arrival curve, A prime of t, can be derived. So the areas between P prime of t and A prime of t will be our queuing delays in the counterfactual scenarios. Then if we put the actual arrival curve A of t from the baseline situations and the model arrival curve A prime of t from the counterfactual and scenarios, we can find the change in arrival delays when removing the MITs. This is a framework of how our method will quantify the impact of MIT on flight delays and the airport throughput. The diagram includes the input data, models, and outcomes. The blue box A, G, and L represent the model, the required input for the data, the individual flight records, the MIT parameters, and the airport and airspace operation conditions. The brown box labeled as D, F, I, K represents the model designed for the assessment, includes the TMI flight matching, predictions on the flight times, and our queuing models for the two scenarios. The green box here represents the intermediate result, and the red box here is our final result on the change in flight delays and the throughput. And in our project, data of TMI restricted flights and their corresponding flight delays are directly provided by matters. So this part of the work have been done, and we need to construct the remainings. Let's first see how we construct the actual queuing diagrams. From the flight level data, the actual arrival times is obtained from the wheels on times. And for the planned arrival times, in theory, it can be calculated from the wheels off times and the estimated time en route. However, for some flight, this results in a time later than the wheels on times. So we redefine the planned arrival times as the actual wheels off times plus the minimum between estimated time en route and actual time en route. Then having the flight times for each flight during the period of time, we can develop the cumulative actual arrival curve and cumulative planned arrival curve and calculate the queuing delays. This is the examples for the real operations for November 26 during 2018 at ORD airport. We can observe some severe queuing delays from 7 a.m. to 2 p.m. in that days. Okay, then the next part is how to derive the model queuing diagrams without MIT in the systems. First, we compute the planned arrival time when MIT were removed. As we only have the flight plan times and actual flight times in the dataset without information on the flight en route performance. So because of limitations on the data, we have tested several different definitions on the model planned arrival times to get the best estimations we could have. For case 1, we directly remove the MIT delay from the baseline planned arrival time. But when setting the flight plan time, that is estimated time en route we mentioned before, MIT delays will not be considered. So case 1 will lead to the model planned arrival time earlier than it should be. In case 2, we will remove the ORD MIT delay from the actual arrival times, but this case ignore the other terminal delays not caused by the MITs. So the setting is underestimated later than it should be. So in case 3, we separate the MIT delay into the MIT ground delays and MIT en route delays. So we recalculate the wheels off times as the actual wheels off times minus ORD MIT ground delays, and the model en route times as the minimum between the estimated time en route plus other TMI en route delays, and the actual time en route minus ORD MIT en route delays. And these definitions can resolve the concerns in case 1 and case 2. In case 4, it is very similar to case 3, but instead of directly use the flight plan times, sometimes could be inaccurate. Different predictive models are applied. The goal of the predictive model is to estimate the en route times without constraints of airport capacities, which indicates flights are not in the queue or impacted by the any MIT en route delays. So we have a filtering procedures applied to the arrival flight first, then developed a general form of models as en route delay. En route times is a function of operational variable, temporal variables, and weather-related variables. And we adopted least square, random forest, and neural network models in our predictions. Now, having the model planned arrival times without MIT, we use it as the input for the queuing models. Here we adopted 2 methods. The first method is a 15-minute aggregated queuing model. Based on the capacities of the airport during each hours, we will allocate the flights into the airport like box fillings against the times. In this case, the change in queuing delays and arrival delays are calculated by taking difference between the counts in each quarter hours and multiplying by 15 minutes. The second method is a flight level multi-server queuing models. It treats the airport runway as multi-servers and serve aircraft based on the runway time availabilities and the flight plan arrival time. Then the service times will be the highways requirement. In the end, we can derive the cumulative model planned arrival curve and the model actual arrival curve and calculate the change in queuing delays and arrival delays. Now let's move to our data set and some relevant statistics. In our project, we have 4 data sets. The first one is ASPM flight level data, which include information on the scheduled flight plan and actual time for individual flights. The second one is airport quarter hour data, includes the operational information and the weather information for each quarter hours. And in this data set, we find that during some quarter hours, about 2% of the time for ORD airport, the observed throughput can exceed the arrival rate. So to make life easier, we make the very straightforward assumptions on the airport capacities as a maximum between the arrival rate and observed throughput. The third data is matter post-processing national traffic management log. It involves all the TMI operations parameters in the national airspace. Then the last one is layered TMI matrix, which captures the delay type and the delay amount for the restricted flight arriving at ORD airport. Each record indicates a delay of a specific flight from a TMI event. Okay, let's see some relevant statistics about ORD MITs. There are over 240,000 MIT caused by ORD in 2018. 57% of them are directly issued by ORD, and 43% of them are passback restrictions. The map here shows the direct restriction frequencies on the surrounding fix or waypoint. The blue dot here represents the ORD output. The red dot here represents fix and waypoint, and the size of the red dot represents the frequencies. And for the spacing requirement, it ranged from 10 nautical miles to 250 nautical miles, while the most commonly used spacing range from 10 nautical miles to 30 nautical miles. Among the restricted arrival flights, 58,000 flight delay events are generated with nearly 8,000 hour delays. The MIT flight delay can be categorized into departure, factorings, and holding delays. And these tables present the counts, average durations, and standard deviations of different delay type. Now we will move to the result and the discussions. The following two tables here summarize the result of change in queuing delays and arrival delays based on different settings of planned arrival times in the absence of ORD sourced MITs. The upper one is derived from the quarter hour, that is our 15-minute aggregated Qe model. The bottom one is derived from the multi-server models. When we compare these two tables, we can see the quarter-hour level models have similar results with the flight level models, but there's also a minor difference. One explanation for the difference is the calculations for the quarter-hour level models is in 15-minute scales, which can lead to some errors. At the quarter-hour level, we can see case 3 has similar values with the case 4, the predictive in route times models. There are about 14.9 to 16.3 hours in arrival delay serving per day, and 1.6 to 3 hours increase on queuing delays per day when we remove the MITs. For the flight level reallocation models, the value for case 3 and case 4 are also close, with saving on arrival delay per day ranging from 14.6 to 16.2 hours, and the increase on queuing delay per day range from 1.7 to 3 hours per day. In addition, the delay change for each flight can be tracked in these models, so we divide the flight average delay into MIT flight and non-MIT flight. So first, for those non-MIT flights, we can say it experience more arrival delays, which mean they tend to arrive late when removing MITs, and also with longer queuing times. And then for the MIT flights, on average, they tend to arrive earlier and experience shorter queuing times if MITs were removed. Now let's have some analysis on the MIT performance. When we model the flight arrivals without MITs, the arrivals in each quarter hour could increase, decrease, or remain the same. Here we compare the quarter hour throughput change between the baselines and the counterfactual scenarios. The change in throughput for a given quarter hours is calculated as the counterfactual scenario subtracted by the baseline scenarios. The figure here presents the change in throughput of quarter hours. Overall, 18% of the quarter hour experienced throughput reductions when implementing MITs. In details, the side-by-side bar chart here shows the sum of throughput gain and loss for each quarter hours when implementing MITs. For example, the yellow box here highlights the throughput change in the first quarter hour of 6 a.m. It seems that the airport during 7 to 9, 11 to 12, 17:30 to 8:30 tend to experience more throughput reductions when having the MITs, and those delay flights tend to be allocated into the later quarter hours respectively. Next, The change in queuing delays and arrival delays can be grouped into day-based, and this graph plots these two delays along the day of the year. The yellow area represents increase in queuing delays if the MIT were removed, while the right areas represent the increase. The red area indicates the decrease from arrival delays. As we can see, for some of the day, the remove of MIT saves substantial arrival delays with minor increase or even decrease in queuing delays, while there are also days with insignificant difference between queuing and arrival delays. Then we further carry out the queuing models for individual MIT at ORD airport. For a single given MIT, we detect its restricted flights and MIT delays, then calculate the model planned arrival time and carry out the flight level queuing models. So the corresponding change in queuing delays and arrival delay can be calculated. In the dataset, there are 13,104 MIT sourced from ORD, which involves restricted flight delay. And the plot here indicates the performance of those MIT restrictions. Each dot represents MIT removals. So we can check the overall change in the queuing delays and arrival delays if that given MITs were removed. From the scatter plot, the x-axis represents the increase on queuing delay. The y-axis represents the saving on arrival delays. And in part 1 of the graph, flights tend to arrive earlier with longer queuing delays when MIT in part 1 is removed. And in part 2, flights tend to arrive earlier with shorter queuing delays when the MIT in part 2 is removed. Okay.
Siri here.
Oh, sorry. This is the majority of the work we have done, and now let's have a summaries. In our project, we proposed and designed a model include estimations on the planned arrival time, deterministic queuing models to assess the impacts of MIT restrictions on the flight delays and throughput. And we use the ORD airport during 2018 as a case study to test our model. The result shows that the operations of MIT at ORD airport leads to certain inefficiency in the national airspace. First, if all the ORD sourced MIT were removed, the overall queuing delays would increase by 3.3 hours per day on average, while the arrival delay would decrease by 14.7 hours per day compared to the actual scenarios in our case 3 flight level reallocation models. And second, during 8 to 9, 11 to 12, and 1730 to 1830, ORD airports tend to experience relative higher throughput reductions when implementing MITs, and those corresponding delayed flights will be allocated into 9 to 10, 12 to 13, and 1813 to 1913, respectively. Third, the vast majority of individual MIT seem to be more efficiency than the MIT in aggregate, which suggests that aggregate performance is strongly influenced by a few bad apples. Here are some limitations and future work. First, when we have the counterfactual scenarios and run the queuing models, we neglect the sector and the terminals and also the controller's capabilities. Second, the model result highly sensitive to the assumptions on the airport capacities, which is a maximum between the arrival rate and the actual arrivals during each quarter hours. Third, the research models are highly dependent on the accuracy of metadata as they provide the TMI delays for each flight for us. In the future, we plan to incorporate a broader range of features into the predictive models on the flight time en route. We can include the convective weather matrix and en route wind effects from the other data sets to improve the predictive modeling. Second, we can develop the predictive model to estimate the capacity of airport or runway so we can release the assumptions on the capacity. Third, our framework and models can be adopted and modified to the other case studies. For example, like MIT operations at other airport or during other period of times. And the model can be further revised to assess the operations of other TMIs based on their characteristic, such as ground delay programs and TBFM. Okay, so this is the content for my presentations. Thank you so much.
Okay, thank you, Kay. Very interesting study. So again, if you have any questions for Kay, please enter them in the Q&A feature at the bottom of the screen. Yeah, so I'll start off. I have a couple of questions. So one is so Miles and Trail as a traffic management initiative. I mean, all traffic management initiatives have different objectives, right, over different spatial and temporal scales, and Miles and Trail is just one of those tools in the air traffic management toolbox. So have you looked at or thought about what impact removing Miles and Trail might have on the need for additional other types of traffic management initiatives in order to manage flows? And I'm thinking particularly when you're looking at, I mean, O'Hare is obviously a big airport in the system, but it's not the only airport, right? And traffic management initiatives impact flights to multiple airports very often. So yeah, have you thought about those broader network impacts of what you've been studying here?
You mean like when we remove the Miles and Trail restrictions, the limitations on the capacity still exist. So to resolve the issues, we will need other TMIs or the management method to deal with it. And
right.
And actually, like having the deficiencies in Miles and Trails because it is a distance-based metering method. It is not that flexible. And now the systems want to like use the time-based flow management, TBFM, as a new TMI designed for the systems in the FA's next gen. But because the techniques is still immature, so the current system is a hybrid systems of TBFM and MIT restrictions.
Yeah. So, I mean, have you as part of your research, have you spoken to any air traffic managers about what some of the implications of removing some of these MITs might be in the broader system context?
No, we haven't speak to any controllers, but we do this based on the literatures and the report we could find.
Okay.
Because in our model, we make the, or we neglect the, like, as I talked about in the limitations, we neglect the workload, the capacities for the in-route sectors and the controllers when we remove MITs and assume they can arrive at the terminal areas as they want. But in realities, we know if there are too many aircraft in the terminal areas in one sector, this cannot be true. And this could be one possible impact from the MITs we don't have in the models.
Right. Because, for example, one reason why Miles and Trail might be imposed is because that the terminal controllers are trying to create spacing in the arrival stream for different types of operations, right? Whether it's departures or merging in arrivals from other airports, you know, creating spaces in flows is one reason why Miles and Trail are imposed. And that actually gets to a question we've just had come in on the Q&A, which is there any interaction at O'Hare between arrival throughput and departure throughput? And do the arrival MITs impact O'Hare's departure rate?
Yes, we have considered this in the research, but have not put it into the actions because in the capacities, we make the assumptions as a arrival rate, a minimum value between arrival rate and observed throughput. And the arrival rate is directly derived from the ASPM quarter hours, which might influence by the departure rate, but we are not consider it. We directly take these values. But in the future models, we want to develop a capacity models which could take into the departure into the considerations as one of the variables. And maybe in this new studies, we can find if any impacts from the MIT can have on the departure rate.
Okay.
But talking about this, the arrival MIT may not have big impacts on the ORD departure rate, but could have impacts on the corresponding restricted flights departure arrival airport, because the MIT can be passed back in route and then passed back to the departure airport to have some ground delays on those restricted flights, which can impact the departure rate at the departure airport.
Right. So yeah, and that kind of gets back to the sort of the broader sort of network effects, right? Of I mean, miles and trail at one airport can often influence operations more broadly, right? And that's I think this is a really interesting and rich area of research because of all these interactions and because of the operational impact that these decisions have. And that's why air traffic management R&D is a rich field to be in, right? So again, if anyone has any other questions, don't be shy about entering them. Have you thought at all about how generalizable do you think your current findings are to other airports? Are there other airports that you think would have similar findings, and other airports that you expect would have very different conclusions from this work?
Oh yes, we haven't carried out the models for the other airports because we do not have the data for the MIT delays for those arrival flights at other airports. But I think the operations, like how the MIT operates at different airports, they follow some same like manuals. They should have some inefficiencies because as we talk about the deficiencies, the MIT are designed based on the predicted capacities and the demand, and the settings is a multiple of 5 nautical mile. It is not very like flexible. This could lead to some inaccurate. But for the ORD airport is a very typical study because it issued the most MIT restrictions during the years, and some other airports, they have less MITs. Maybe the MIT will have less impact on their arrival delays and the queuing delays.
Yeah. Okay, we've had a couple of new questions come in. One is, your analysis shows that there are many more MITs than GDPs, ground delay programs. Why do you think this is?
One explanation is how people record MIT and GDP. For GDPs, if we have the very large imbalance between the airport capacity and demand a few hours before, we will implement the GDPs. And when GDPs is record, and inside that one GDPs, it will have the delay aside for the multiple arrival flights at from different airports. And this is one GDP. So one GDP involves a lot of arrival flights from the departure airport surrounding. But for the MIT restrictions, one MIT restriction is recorded as the spacing requirement at a fixed or waypoint. So in that case, we have an imbalance at the airport. Now we want to have MITs. And for the waypoint or fix around, one restrictions is recorded as one MITs. So this is one possible reasons, it is more GDPs, much more MITs than GDPs. But
Okay.
when we're checking the data, the MIT delay and the GDP delays, the GDP delay is much, much larger than the total durations of MIT delays.
Okay, so the quantity of events versus the impact in delay can be different, right?
Yes, like
okay.
for GDPs, usually for each flight, like several hours of delays,
Yeah.
but for MIT, sometimes it's just a few minutes.
Oh, right. Yeah, that makes sense. Another question, can you further describe how MITRE assigns delays to aircraft because of a specific mile and trail? Does it include both trajectory and ground delays?
Sorry.
So yes, this is a question about the MITRE data set that was one of the inputs to your work and how delay is being assigned within that data set to a given MIT condition.
Yes, like in matters data, they measure the MIT delays as a ground delay, factoring and holding delays. So for each MIT restrictions, we have the parameters of durations and where it happens, like the fixed point or waypoint or the departure airport. Then for the ground delays, they measure the ground, they have the ground delay information for each flight, and they match the occurrence times of the flights with the durations of the MITs. See if it match. This part is easier. Then for the vectorings and holdings, I have discussed with matters before. They told me they have some in-house algorithms with the vectorings and holding flights in their data set. So where the vectoring and holding delay happens, when and where the vectoring and holding delay happens for each flight can be tracked in their data set, I think. Then they match the locations and the times for those vectoring and holding delays with the MIT parameters. So then if they match, they will detect it as the MIT delays for that given flights. But in our data set, what we observed is a record of the flight delays resulted from MITs or from other TMIs directly.
Okay. So yeah, so that sounds like a really interesting data set that you had access to there.
Yes.
So I guess MITRE ran in post-process to identify where the delays were being apportioned. Is that right?
Yes.
So after the operational day had happened, they run the data through their algorithms, and that identifies where the delay is happening.
Mm-hmm. I think the inputs of the algorithms will be the MIT parameters, the durations and the locations. Then they have the flight data for vectorings and holdings they input into the algorithm to match.
Okay. All right. We are very close to the end of the session. We're at yeah, we're within a minute of the end time. So I think I see no other questions. Okay, thank you very much for a very interesting presentation and for answering our questions. So that wraps up the first part of this ATM performance session. We're going to have a coffee break now. I'm just checking the agenda. So we will be back in 10 minutes for the second part of this session. I just want to thank our two speakers again for two very interesting briefings. Part two of the session, starting in 10 minutes, will be chaired by Guillermo Lully.